Thank you very much for the wonderful introduction. So I'm Tori Miller. I lead the Monster Research Group at the University of Florida. This is our mascot. Let me pull up a laser pointer. This is our mascot. His name is Dorcas. And I want to thank the National Science Foundation because most of this work has been supported by the National Science Foundation. Before I go any further, I also need to acknowledge my research group. None of this work would happen without them. In particular, I want to acknowledge Justin Norkett, who is here. Justin is the grad student that primarily works on the liquid metal embrittlement project. So these are a lot of his results. Now, before I jump into the major part of this talk, I want to give a little bit of background on what my research group does. Fundamentally, what we're interested in is bridging the mesoscale gap. We're interested in quantitatively linking the macroscopic processing, say forging, to nanoscale crystalline defects using advanced characterization techniques. So that's things like SEM, TEM, calorimetry, electron backscatter diffraction, etc. The other major thrust within my research group is developing infrastructure for integrated computational materials engineering. So we've done things like written some code that links deform macroscopic finite element software with B.S.E, the viscoplastic self-consistent polycrystal plasticity model to get site-specific texture evolution. We've also made a tool that's similar to WebPlot Digitizer for pole figures. So if you're interested in capturing historical texture information, you might want to check out our tool Dragon that we recently deployed. If you're interested in any tools like this, you should check out our GitHub, which is github.com/monstergroup. Also, if this is the sort of work that you're really interested in and excited about, you might want to check out the upcoming conference and submit an abstract to the 7th World Congress on Integrated Computational Materials Engineering, ICME 2023, which is happening in May of next year. Now, along those two lines, bridging the mesoscale gap and developing infrastructure for ICME, we work in a lot of material systems. We work in magnesium, trying to look at how the microscopic deformation mechanisms result in brittleness so that we can avoid brittle failure. We look at nickel superalloys to make turbine engine disks that can operate for longer times at higher temperatures. Similarly, we're interested in titanium, also for gas turbine engines. And then additionally, we have a project on using lasers to form sheet metal like sheet aluminum. So you can see that you can cut and fold all in one laser process to get a nice little cube. Today, though, I'm talking about a different project, talking about liquid metal embrittlement and cracking open the disparate mechanisms. I got really excited about this when my collaborator, Michael Dickey at North Carolina State University, showed me these videos. So this is a stretchable electronic device. So these are headphones that have a liquid core so that inside an elastomer shell so that you can go ahead and stretch them. Additionally, you can go ahead and use microfluidics to pattern these liquid metal electronics. So this is liquid eutectic gallium indium, and this is just PDMS with microfluidic channels built in. And you can see that this student is using a syringe to fill the channels. And once the channels are filled, you have this completely flexible, stretchable device. You can fill complex shapes like spirals. And then this down here is actually a flexible thermoelectric device. This is really interesting, and you can do all sorts of neat tricks, like you can use electrochemistry to manipulate the oxide and alter the flow of the liquid metal. So when you apply a voltage, you increase the thickness of the oxide, causing your puddle of liquid metal to bead up. Inside a PDMS channel, this can be used to create flow into or out of particular channels. So in this case, they're applying a voltage, and just the same way that the liquid metal, the eutectic gallium indium, wanted to bead up before, you can see it is trying to bead up by flowing backward through these channels. So this is all well and good. This is very neat, but there are all sorts of other applications of liquid metals as well. You've got things like advanced nuclear reactor concepts, both fission and fusion reactors. You've got mercury in natural gas processing plants, because when you pull natural gas out of the ground, it actually has a lot of mercury vapor in it. So liquid metals are all over the place in advanced energy applications. However, liquid metals can be scary, and not necessarily for Terminator-related reasons. Liquid metals, when in contact with certain solid metals, can create embrittlement and catastrophic degradation of material properties. So here is a GIF of gallium on an aluminum soda can. And you can see once the soda can has been exposed to gallium, it's very brittle and you can just punch your finger right through the top of it. This is an aluminum heat exchanger that was exposed to mercury vapor, or condensed mercury vapor, so mercury liquid. Note the scale bar, this is 500 millimeters, so this is half a meter long. And you can see catastrophic failure. And this over here is a piece of bulk aluminum where this half was exposed to a eutectic gallium indium mixture. And you can see that it just sort of disintegrated into this pile of gray dust. So when I saw Michael Dickey's really exciting demos on stretchable electronic devices, all that I could think about is all the times that I have done something like this to my charging cable or my headphone cable, where I've destroyed my liquid metal, or where I've destroyed my electronic cable. So what happens when you have a stretchable electronic device and you damage it and the liquid metal gets out? Fundamentally, the question that we want to ask is, how do we predict liquid metal embrittlement so that we can prevent engineering failures? Now, if we only look at the literature, there are some relatively reliable trends that exist. So, for example, in this particular case, you can look at the engineering strain and the engineering stress, and materials that, if you look at the electron per atom ratio, or rather the value of Pauling electronegativity, as you increase the electronegativity, you get greater strain and greater stress at failure. So that's one reliable trend that looks good. Over here, you can look at the electron per atom ratio, and you can look at the stacking fault energy, and you can say, okay, when we look at the fracture stress in mercury normalized by the fracture stress in air, divided by the flow stress in air, you can see distinct trends that emerge here. However, all of these trends tend to be sort of limited to within a single system. If you start digging deeper into the literature, you start seeing contradictions. So if we look at the sensitivity of liquid metal embrittlement to prior strain, so on the x-axis here, we have some measure of prior strain. And then on the y-axis, we have some measure of strain to failure. In this system, the copper mercury system, you get worse performance after prior deformation. Whereas in this system, leaded steel, you actually get better performance, increasing strain to failure after prior deformation. And this is emblematic of sort of every liquid metal embrittlement rule that's been proposed. They all have numerous exceptions. It's very confusing, or it seems to be. Another example is some systems are time dependent and others are not time dependent. So this is aluminum and a copper zinc alloy in mercury. Here you can see that as time progresses, the fracture stress doesn't change at all. Whereas when you expose zinc to mercury and varying amounts of mercury, the fracture stress is very sensitive to the pre-exposure time. So some systems are time dependent, some are time independent, some get better with prior strain, some get worse with prior strain. A lot of contradictions in the literature. So our next thought on how to tackle this was, what about just using an empirical approach? What about pure empiricism? So I want to give a shout out to, again, my grad student here, Justin Norkett, because he went through something like 1,500 different papers and set up this table. And this table is different solids exposed to different liquids. And it's just an indication of whether things have embrittled or not. The problem with this notion is that if you, again, dig a little bit deeper into whether things have been reported to embrittle or not, many systems have been declared non-embrittling based on a single test. So again, this is the same sort of table. These are all different solid metals exposed to different liquid metals. And anything with a letter has been declared non-embrittling. The problem, though, is that anything shown in blue has very limited testing. Anything shown in red was only tested at a single temperature. Anything shown in green, they reported it as being non-embrittling, but they didn't report any information on how the test was conducted. And then anything shown in orange has also been reported later as an embrittling system. So to sum up sort of this brief sprint through the literature, we can't make predictions. We can't settle on the basic phenomenology, and we can't trust when we designate systems as non-embrittling because it's often based on just one test or very limited testing. So with all of that in mind, how do we predict liquid metal embrittlement? So we proposed a bit of a framework to interpret this. We propose that liquid metal embrittlement has microstructure dependent and microstructure independent components. And we propose that liquid metal embrittlement has multiple separable mechanisms. And sort of the rest of this talk is going to be demonstrating those 2 points for you. So first, microstructure dependent and independent parts. Looking here, this is molten tin on zinc And this is temperature versus elongation to failure. So here, we get a lot of elongation to failure at low temperatures. We get low temperature plasticity. When we increase the temperature somewhat to about 200 C, we get embrittling behavior. Note that this happens right near the zinc tin eutectic temperature. But then as we continue to increase the temperature, thermally activated plasticity starts occurring. So we get ductile behavior again, and we start getting more elongation to failure. So this is the way to think about this, is that there's an intrinsic chemical susceptibility to liquid metal embrittlement. That's why you do get embrittlement. But then there are mitigating and amplifying factors. So things like thermally activated plasticity. You can see this same sort of behavior, and I know this plot's a little bit busy, but you can see the same sort of behavior with strain rate. So each different plot here is a different strain rate, and each different color is a pair, or each different color is a pair strain rate, no strain rate, and each different color is a pair with or without gallium. So in all of these different systems, you see at low temperatures, you get very little ductility. Whereas at higher temperatures, your ductility is restored because of thermally activated plasticity. And that's true at different strain rates. That's true with and without gallium. So all of the no gallium samples fall along this line. All of the gallium samples fall along one of these three curves. And you can see that at each different strain rate, embrittlement is more or less severe. So at these low strain rates, embrittlement is less severe because there's more time for thermally activated plasticity to be active. Whereas at these higher strain rates, there's less time for thermally activated plasticity, so you get this much wider ductility trough across different temperatures. And you need to get to a much higher temperature before ductility is restored. So that's the first half. There's microstructure dependent and independent parts. The second half was that there were multiple separable liquid metal embrittlement mechanisms. And we propose 3 mechanisms, or we propose a minimum of 3 mechanisms. There may be additional mechanisms that haven't been fully described yet. So the first mechanism that we propose is liquid metal assisted cracking. This is a lot like stress corrosion cracking, but in a liquid metal environment. The second mechanism we propose is grain boundary infiltration, or grain boundary wetting. So your liquid wicks along the grain boundaries, and then because you now have a liquid at your grain boundaries, your material no longer has any mechanical strength because you can't apply tension to a liquid. And then the third class of mechanisms is liquid metal corrosion. And this could be selective leaching from the alloy, or this could be formation of a corrosion product either within the grains or within the grain boundaries. And I'll show you a little bit more information on what each of these proposed mechanisms looks like. So liquid metal assisted cracking looks a lot like this. You can get intergranular cracking or transgranular cleavage, depending on what system you're looking at. So these are both zircaloy, but in cadmium, you get intergranular cracking, and in silver, you get transgranular cracking. In both cases, you get this characteristic stress strain behavior where overall, your yielding behavior is similar with and without the presence of liquid metal. You may actually get a slight increase in yield strength because of solute effects and some solid solution strengthening in the liquid metal. However, you get a catastrophic reduction in ductility. This particular liquid metal embrittlement mechanism is very temperature sensitive. So again, this is our tin on zinc plot. Embrittlement only occurs in this relatively narrow 50°C window. And again, this is gallium on 60-40 brass. Depending on your strain rate, your embrittlement may only occur in a 30-degree window or in a 100-degree window. So it's very sensitive temperature. You get multiple temperature transitions. The second proposed mechanism is grain boundary infiltration. So this would be wetting of the grain boundaries. What this looks like is you get uniform wetting along the boundaries. You don't get any apparent deformation within the grains, and you don't get any wedging. So you don't get any variable thickness of the grain boundaries in any meaningful way. So looking at this aluminum specimen that was exposed to gallium, you can see that the plate-like morphology of the grains because it is an as-rolled plate, and you can see it literally peeling apart at the layers between the grains. And then in this bismuth nickel specimen, you can see uniform film of liquid sitting along the grain boundaries. And then the final mechanism is liquid metal corrosion. So this is eutectic gallium indium liquid on gold. And as you can see, there's a lot of stuff going on. There's formation of various intermetallics. There is local oxidation. There is this puddle of liquid that has small crystals growing within it. There's a lot happening. You can also get a much simpler morphology. This is my favorite example because this example is molten plutonium on a tungsten rhenium alloy. And you can see you get a surface film of corrosion, and you get selective grain boundary rhenium depletion. And if you look at the grain boundaries, they have this characteristic wedge shape because depletion is more severe near the surface than it is toward the interior of the material. So to summarize, we've got multiple separable liquid metal embrittlement mechanisms, and we may get cooperating and both cooperation and competition between these mechanisms to see which mechanism or mechanisms dominate the overall behavior. When we look at liquid metal embrittlement through this lens of multiple mechanisms, some of these apparent contradictions in the literature start to actually make sense. So when we look at liquid metal corrosion versus interfacial cracking, this is the same strain prior to exposure and some measure of ductility. In this case, in the copper mercury case, deformation increases the reactivity, so you get worse performance after prior deformation. Whereas in this case, the leaded steel, deformation increases dislocation availability, so you get better performance after prior deformation. That's the difference between something like liquid metal corrosion, where reactivity is your primary concern, versus interfacial cracking, where dislocation availability is your primary concern. You can also look at a plot like this, where the phenomenon, so this is polycrystalline aluminum, this is temperature, and then this is the strain to failure. And each of these curves is a different amount of gallium in mercury. So over here is pure mercury. This curve is 4 atomic percent gallium in mercury. And then if you'll note down here, this is the 100% gallium curve. This is a transition from an interfacial cracking mechanism to a grain boundary wetting mechanism. Gallium fully wets the grain boundaries. And as gallium starts to wet the grain boundaries, you get this wedge that acts as a pre-crack. So you get more severe embrittlement. Whereas gallium, pure gallium, is full grain boundary wetting, which is why you get very little temperature sensitivity and complete embrittlement. So again, let's go back to this sort of core proposition. I've shown you some evidence that LME has microstructure dependent and independent components, and some evidence that LME has multiple separable mechanisms. Now I'm going to show you a little bit about cooperation and competition to dominate behavior. The first bit of this is going to be about grain boundary wetting. And then the second part will be about competition between grain boundary wetting and liquid metal corrosion. So let's start with just a story about grain boundary wetting. This right here is zinc exposed to eutectic gallium indium after we attempted to pick it up with tweezers. You can see that these are all individual little grains, and it literally just fell apart at the grain boundaries as we tried to pick it up with tweezers. We looked at this in situ in the SEM as the eutectic gallium indium was infiltrating the zinc. And you can see all sorts of things happening in this microstructure. You can see new crystals form and grow. You can see indium precipitating out. And you can see some boundaries that have not wetted yet undergoing a wetting transition. There is complete penetration of this grain boundary network by the liquid eutectic gallium indium. Eutectic gallium indium is E-gain. Note that this is all occurring over the course of an hour, and it's all occurring at room temperature. So the rate of grain boundary penetration depends on grain size, but not so much on prior deformation. So we looked at we looked at a few different microstructures. We looked at a fine-grained microstructure and a coarse-grained microstructure. And we considered 0% rolling reduction, 10% rolling reduction, and 45% rolling reduction. The coarse grains all followed one curve, regardless of your rolling reduction, and your fine grains all followed a different curve, regardless of rolling reduction. And note, you get a linear grain boundary penetration distance with time. When we were looking at some of these videos, though, we started seeing some really interesting behavior. So if you focus on this circled area right here, it looks like you actually get the nucleation of a recrystallized grain mediated by the presence of liquid at the grain boundaries. So we wanted to look at this a little bit more clearly. So we started by overlaying some electron backscatter diffraction with this GIF of grain boundary penetration. So you can see the liquid eutectic gallium indium starts off here on the left, and it penetrates the grain boundary network to the right. And I'll let this play again. And we looked at the microstructure pre and post exposure to eutectic gallium indium. Pre-E-gain exposure, you have a lot of relatively coarse grains that have a lot of internal strain. After E-gain exposure, you get a lot of very fine grains, none of which have significant internal misorientation. And you can see the amount of internal misorientation on these grain orientation spread maps. You'll note that you do get much poorer indexing in the liquid infiltrated specimen because the liquid fraction of the material no longer diffracts. Note that this same effect is present, but only weakly present when you have a 10% reduction in thickness versus a 25% reduction in thickness. At 10%, you don't have the critical strain to initiate recrystallization. So this is very interesting. This is a relatively new recrystallization mechanism. I'll note that we are not the only people that have observed this. This was previously observed in SAC. So this is a lead-free solder that was exposed to gallium. The initial grain structure of the solder ball started out very coarse. And then when exposed to gallium, you got recrystallization into this much finer structure, either partially recrystallized when exposed at 70 C for 15 minutes, or fully recrystallized when exposed at 110 C for 15 minutes. And then there was this one other thing that we noticed in this same GIF. We saw these interesting crystals that seem to be growing in this puddle of eutectic gallium indium. And you can see these growing and intersecting, and you can see some more showing up over here. And we're very curious about what exactly these were. So when we exposed a much smaller volume of liquid so that all of the liquid was absorbed, you actually got big platelets of basically pure zinc that were growing. So these growing crystals are large platelets of pure zinc that dissolved into the liquid and then reprecipitated out. So that's very interesting. And unfortunately, I don't have the time to talk about it further right now. Happy to answer questions about it later on, though. The main takeaway, though, is that grain boundary wetting can facilitate recrystallization. So you might be able to use this for, say, amalgam replacements for dental work or other places that you use mercury amalgams. Now, the last part of this that I want to show is that we can shift the mechanism of liquid metal embrittlement via chemistry. And when I say the mechanism, I mean the dominant mechanism. So this is an aluminum alloy. This is 5052 aluminum. At the top, it's exposed to pure gallium. At the bottom, it's exposed to eutectic gallium indium. At the top, you can see you're getting just nice grain boundary wetting, and you can see the front propagating across the specimen. At the bottom, you're getting oxidation, and quite a lot of oxidation that propagates across the specimen. And that is just by adding a little bit of indium to your liquid metal. The other interesting thing is that we can shift the mechanism via environment as well. So we can shift from grain boundary wetting to liquid metal corrosion just by modifying the humidity. So this is that same GIF that I just showed. This is Florida ambient humidity, so about 70% in the lab, versus in a dry box, we ran the same experiment. So at about 20% humidity, you get grain boundary wetting, whereas at 70% humidity, you get oxidation corrosion. So we can shift what mechanism is active by modifying the environment. I'll note that mercury on aluminum displays very similar behavior. This is the fairly famous Nile Red YouTube video where you get growth of this mercury, of this aluminum oxide tower when the aluminum is activated by mercury. And it may or may not play real quick, but if it doesn't, that's fine.
In real time, this process is really slow. So I set things up for a time lapse. So
you can see propagation of this liquid metal front going across the aluminum specimen. Here it is at slightly higher magnification. And you can start to see that microstructure dependence of this rate of attack shows up. So both for oxidation and for the grain boundary wetting mechanism. So if you look at the rolling direction, which is vertical here, and the transverse direction, which is horizontal, you can see that in each of these cases, you get propagation faster along the rolling direction than you do along the transverse direction. You get a very slightly different rate of attack. And to prove this is true, to prove to ourselves, we started with an elongated droplet, a droplet elongated in the transverse direction. And at the end of this oxidation exposure, not only did the rolling direction keep pace with the transverse direction, it actually outpaced it. So regardless of the morphology of your starting droplet, your rolling direction propagation goes faster. The other thing to note here is that corrosion accelerates the propagation rate. And our hypothesis here is that you're getting grain boundary wedging that leads to cooperative attack. So as the formation of the corrosion product wedges your grain boundary open, that allows the liquid metal to flow in more easily. But that's still the subject of ongoing study. So that's where I'll leave things. Hopefully what I've convinced you of is that liquid metal embrittlement has microstructure dependent and microstructure independent components. At least 3 individual mechanisms exist under the liquid metal embrittlement umbrella. And separating these mechanisms is the first step in actually predicting liquid metal embrittlement for the first time, because separating the mechanisms starts to resolve some of this seemingly contradictory behavior. Again, I'd like to thank NSF for sponsoring this research. I'd like to thank the organizers for this invitation to present today. And I'd like to thank my research group and my collaborators for helping to support this research. And I'd be happy to take any questions, either now or via email.